Why is amplifier efficiency a trade-off with signal quality? Imagine trying to get the most power out of an amplifier while keeping the sound crystal clear. It's like balancing a scale between two important goals. When you boost one, the other often suffers. That's because of how amplifiers work in signal processing and control systems. Let's start with what efficiency really means. It's how well an amplifier turns electrical power into the amplified signal. If an amplifier is very efficient, it wastes less energy as heat. But if it's not efficient, more power turns into heat, which isn't good for the device or the environment. Signal quality, on the other hand, is about how accurately the output matches the input. When you send a clean, undistorted signal, you get high fidelity. But if the signal gets distorted or loses its shape, the quality drops. In analog signal processing, different types of amplifiers handle this trade-off differently. The most basic type is called Class A. It conducts current all the time through the entire input cycle. This means it produces very little distortion, so the signal stays clear. But because it's always on, it wastes a lot of power as heat. Its efficiency is usually only around 10 to 25%. Next is Class B. It conducts current only during half of the input cycle. This makes it more efficient, reaching up to about 78.5%. The problem is, at the point where the two halves meet, there's often a small glitch called crossover distortion. This causes a slight loss in signal quality. Then there's Class AB, which is a middle ground. It conducts more than half but less than the full cycle. This reduces crossover distortion and improves efficiency. Compared to Class A, it's a good compromise for many applications. Some amplifiers, like Class D, switch the output transistors fully on or off very rapidly. This switching method can reach efficiencies above 90%. But it needs extra filtering to smooth out the signal, and if not done carefully, it can introduce distortion. The core reason for this trade-off is that high efficiency requires the transistors to operate in switching or partially conducting modes. These modes are nonlinear, meaning they distort the signal. To keep the signal linear and true to the input, the transistors must stay in their linear region, which leads to more power waste as heat. In control systems and analog signal processing, choosing the right amplifier depends on what's more important: saving power or maintaining signal quality. For high-fidelity audio or sensitive measurements, engineers prefer Class A or Class AB amplifiers, even if they waste more energy. For battery-powered devices, efficiency becomes more critical, so they might use Class D or Class AB. So, in simple terms, boosting efficiency often means operating the amplifier in a way that introduces some distortion. Keeping the signal pure and accurate means operating in a linear mode, which uses more power. That's why these two goals are often at odds in amplifier design.